During this session of horizon scanning. If you have any questions at any time for our amazing speakers, please add them to the Q&A box, and I'll read them to each speaker at the end of their talk. So I see some more people coming in now, so we'll just get started. Our first speaker of this session is Nicole Kester from the University of Ottawa, who will be forecasting the spread of dog-strangling vine. Thanks so much, Nicole. You can start sharing your screen.
Hi, thank you for having me. My name is Nicole Kester. I'm a master's student at the University of Ottawa, and today I'll be talking about some work done with Heather Karuba and Tyler Smith on forecasting the spread of dog strangling vine in North America. So first, to start with some background information, dog strangling vine, or DSV for short, is an aggressive invasive species from Ukraine and southwestern Russia that established in southern Ontario and the northeastern United States beginning around 1900. In Ontario in particular, the spread of dog strangling vine has led to a decrease in plant, insect, and soil biodiversity, and it's able to outcompete many native species. You often see it wrapping around itself or around other plants. One of the things that makes dog strangling vine so problematic is how difficult it is to control once it has established in an area. If it's not properly removed, it can regrow from the root, and the biocontrol method that we have is not very effective. Because of this, it's important that we identify regions that are at risk of invasion by dog strangling vine before it spreads there. From previous work, we know that dog strangling vine has reached environmental equilibrium distribution in its invaded range in North America, which just means that it is not establishing in new types of environmental conditions. It is, however, continuing to expand its geographic range. There is still a lot that isn't known, such as whether dog strangling vine's environmental niche is the same in its native and invaded ranges. Our goal was to model the potential distribution of this species across North America now and in the future to help guide prevention and control efforts as it continues to spread. And in addition, the project provides the opportunity to examine the importance of niche shift analysis for a highly invasive plant species on forecasts generated by species distribution models. So we'll start by looking at where dog strangling vine is right now. There's a lot of occurrence data available from GBIF, including herbarium records and citizen science data, and there are other citizen science databases such as EBMAPS. We can see that most occurrences are clustered around southern Ontario and Quebec in the northeastern United States, but that the species is beginning to spread, for example, into Atlantic Canada and northern Ontario. Next, we want to know what environments dog strangling vine occupies, and to do this, we use occurrence records and environmental data, and by making associations between them, we can quantify the set of environmental conditions where we have found dog strangling vine. This is our starting place to try to understand what climates are suitable for dog strangling vine. We did this for the native range and for the invaded range, and we want to determine whether this species occupies the same types of environments in both ranges. We performed a principal component analysis of our bioclimatic variables and used the first two axes of this PCA to define environmental space. We used 19 bioclimatic variables available from WorldClim, which represent various measures of temperature and precipitation. This then allowed us to plot the environmental conditions where we see dog strangling vine in its native range and in its invaded range. The outlines on the left in red and in green show us all of the environmental conditions available in the areas we're comparing, whether occupied or not, red being the invaded range and green being the native range. In red in the middle, we see conditions occupied only in the invaded range. In green is conditions occupied only in the native range, and in blue is conditions occupied in both ranges. From this plot, it's easy to see that dog strangling vine's niche has shifted significantly between its native range and its invaded range. Interestingly, 2/3 of dog strangling vine's current environmental niche in North America is not occupied in its native range, even though these environmental conditions are present in the native range. This is indicative of a niche expansion, which is important because it means that we're seeing local adaptation, a shift in biological interactions, or some other factor that is allowing these species to access environments that it previously did not occupy. From there, we can use what we know about what environments are suitable for dog strangling vine and translate this to suitability across geographic space, in this case, North America. This is done through species distribution modeling. Species distribution models are a commonly used tool to predict the potential ranges of invading species based on associations between species occurrence records and environmental conditions in their native or invaded ranges. An important assumption of these models is that the species niche does not change, meaning that the species will occupy the same environmental conditions in the future as it does right now. The reason that we looked for a niche shift in dog strangling vine is that this would help us decide whether data from the native range or invaded range is more appropriate to use to forecast dog strangling vine's potential distribution in North America. So this figure shows which parts of North America could be suitable for dog strangling vine based on its current invaded range if it continues occupying the same environment in North America as it does right now. We took an extra step of identifying the parts of North America that are environmentally novel or non-analogous compared to where we currently find dog strangling vine. On this figure, those areas are shown in dark gray. Non-analogous environments represent places that are environmentally very different to the current range of dog strangling vine, so we can't make comparisons, and really, we don't have enough data to predict whether these areas could be suitable for the species, and because of that, we excluded them from model projections. These species distribution models were built with Maxent, which is an algorithm designed for presence-only data. Since we saw that dog strangling vine's niche was different in its native and invaded ranges, we would then expect that our species distribution models would generate different results depending on which range we use to train the model. This is exactly what we see here. Models differ in their predictions of habitat suitability across North America, though both have high Boyce indices, which is just a metric of model accuracy used for presence-only data. The invasive trained model predicts that over 1.5 million square kilometers of North America in current day are suitable for invasion. And this amount is a lot more than dog strangling vine's current range in North America, which looks like this for comparison. Though the invasive trained model is likely better to predict the future distribution of dog strangling vine near where it is currently found in North America, we can't predict what could happen in the parts of the continent that are environmentally different or non-analogous compared to Southern Ontario and the surrounding areas, for example, in Western Canada and in Northern Canada. There, it is possible that dog strangling vine's niche could be more similar to the native range niche, in which case the native trained model could help to give us some predictions for what we could see in farther parts of the country. This is likely not as good a model as the invasive trained model, but it is more broadly applicable. Also, there is a lot less area of North America that is non-analogous to the native range, meaning we are able to generate predictions across a wider geographic area, as we see here on the left. Even if we need to be careful about using data from the native range, given what we know about the niche shift that has occurred between the native and invaded ranges, the native trained model can still generate some predictions, which we can then monitor. We also projected these models forward to 2060 under a high emissions climate change scenario. These models predict a higher total area of suitable environments for dog strangling vine, and as well an increase in suitability of areas that are currently predicted as moderate or low suitability. So areas that are currently low or moderate could become moderate or high suitability. We also see in the projections a northward shift of suitable areas. Regions with the highest susceptibility to invasion include Atlantic Canada, the American Mid-Atlantic, and also some areas in Western Canada and the United States, depending on which training area we use for our models. Finally, for the future climate scenarios, we see an increase in non-analogous areas, meaning that there's more geographic area for which we cannot generate predictions with the current data. So there are some findings that we should consider from these models in regards to how we can manage the spread of dog strangling vine. From the models, there appears to be a large stretch of area in the middle of the continent that is not suitable for dog strangling vine, But if it can overcome this barrier, for example, by human-mediated transport, it does have the potential to establish in Western parts of North America from what we can see in the native trained model. What this means is that we should really make efforts to prevent dog strangling vine from reaching the western side of the continent, for example, by increasing awareness of this risk and by establishing early detection programs. Overall, the regions we identified as suitable for dog strangling vine should be prioritized for efforts to prevent its establishment, as, like I said, the species is very difficult to control after it has established in an area. From a modeling perspective, what we have learned from this project is that in dog strangling vine, there has been a considerable niche shift between the native and invaded ranges, and in particular, a large portion of environmental space of the invaded range niche is present but unoccupied in the native range, which is indicative of a niche expansion in North America. As a result, predictions generated by species distribution models differ greatly depending on which range the models were trained on. This type of niche shift analysis has the potential to be used in decision making when forecasting distributions for invasive species and can help to inform our predictions. Finally, we should continue to track the niche dynamics of the species over time to improve predictions and also to inform monitoring for early detection. Thank you so much for listening, and I'm happy to take any questions.
Thanks so much, Nicole. That was a really great talk. If you have any questions for Nicole, please pop them in the Q&A box and I can read them out loud. Yeah, just kind of looking through what you were talking about, how there's a northward shift in habitat suitability with climate change. It's unfortunate, it's kind of a common theme, I feel like, with invasive species, but it's good to think about now and think about ways that we can kind of help prevent that spread.
Yeah, absolutely.
I don't see any questions coming in now, but we do have a doc with all of our speaker emails. So anyone that thinks of a question maybe afterwards can go ahead and email Nicole directly. There
Yeah.
is a question that popped in here. What biological controls have been released?
So there is one type of moth that's been used, but it's really not very effective. It's quite limited in its ability to be used as a biocontrol method for dog strangling vine. I think that there are other things that are still being looked into, but yeah, so far not really much,
Yeah, that's
which
good
is
to
why
know.
we
Yeah,
really should focus on awareness and prevention.
absolutely. Yeah, biocontrol is amazing, but it can also take a long time to really figure out and research and
Yeah,
yeah, so
exactly.
okay, I'm not seeing any other questions.
All right. Well, thank you so much. My
Yeah,
email's on the screen if anyone has any questions.
perfect. Thank you so much, Nicole. I really appreciate your time.
Thank you.
Okay, so next up we have Joseph Stinziano from the Canadian Food Inspection Agency. He'll actually be our second and third speaker today for this session, but his first talk will be about quantitative horizon scanning in Canada. Thanks so much for joining us.
Thank you, Madison. Hi, everyone. My name is Joseph Stinziano. I'm from the Canadian Food Inspection Agency, and I lead the Plant Health Analytics Hub, where we provide modeling and statistical support to help protect plant health in Canada. Before I dive into the presentation, I just want to acknowledge the others who have contributed to this project. For data and modeling support, there's Wan Ying, Megan, and Josh. And then we had risk assessors review and validate the results of these horizon scans. So that includes Martin, Karen, Alexandra, Rositza, Abdul, and Heather. So with that, let's dive on in. We've been talking about invasive species, and I'm sure that we're all aware that biological invasions are expensive. In the past 40 years or so, the costs of biological invasions rival that of natural disasters, including storms, earthquakes, and floods. And so, as has been the theme throughout today, it's important to focus on that prevention aspect. If we can figure out ways to set up early warnings to be able to prevent things from entering into Canada, we'll be able to best mitigate their potential for spread and damage. And so this horizon scanning is really about trying to get us into that preventative space, making us aware of threats before we're likely to be aware. So I'm sure that some of you have seen horizon scans and saw presentations on horizon scanning. But what is quantitative horizon scanning? So this is a data-intensive systematic search to identify potential emerging threats. The objective here is to identify potential pests early and often to be able to prevent and prepare immediate responses for them. To do this, we identify target taxa, risk criteria, and data sources. And our goal is to identify those potential pests before we would typically consider regulating. And it can help us identify gaps in biosecurity. I'll note that there are existing horizon scan methods that are time intensive, requiring a lot of people's time, or they don't produce readily actionable results for national plant protection organizations such as CFIA, USDA, APHIS, or they're non-quantitative. In terms of pest risk analysis at the CFIA, there's a few different steps. What I'm going to be presenting right now is a new step we're adding that's really focused on using data for foresight. But below that, I'll run through how the pest risk analysis process typically works. There's an initiation, either due to pest interception or request for importing something, or importing a new pest from elsewhere. Then there's a categorization that's done to determine if it's a potential quarantine pest or not. It then moves through a risk assessment that looks at the probability of entry and the consequences. And if it proceeds past that, it goes into risk management that takes into account other factors like the acceptability of the risk, trade or stakeholder considerations, availability of mitigation options, feasibility and cost benefit. And then if it goes ahead for regulation, it goes in this measure section where we have to notify stakeholders, the World Trade Organizations, and so on. Now in this foresight piece, this is where quantitative horizon scanning is feeding in. In terms of the framework that we're using a combination of a high throughput risk quantification framework and a semi-quantitative risk analysis tool. For our risk quantification, we use climate data and species occurrence data to do climate modeling and run some self-organizing maps, which take into account how species assemble together to try and predict where they could invade elsewhere in the world. And then we also look at invasive species trait data, pathways, and dispersal information. Megan on my team has been developing a really good spatial ecosystem services data set that we're using, as well as looking at trade data. These are then combined in the risk analysis tool into 4 different categories: geographical potential, where in Canada it may be able to spread; establishment and spread potential, these are factors that contribute to an organism's ability to actually spread throughout its potential niche; entry potential, what's the likelihood that it will actually come into the country based on trade and natural dispersal factors; and then impact potential. Once it's here, where is it going to have an impact within Canada? Those are then all combined into a scoring and ranking. Now, the semi-quantitative risk analysis tool that we're using was developed by the USDA for weed risk analysis, and we're now adapting it to other taxa. So we've run 2 horizon scans so far. The first one was on wood-boring beetles, and we had taxonomic grouping that's shown here. It does include some off-target species that aren't exactly wood-boring, but it represents the simplest way to generally capture wood-boring species. And the second scan, we focused on invasive grasses, and we looked at the entire family Poaceae. I'm going to be presenting the results of that scan because that one is the most sophisticated in our data pipeline. When we do the climate modeling, which we use the CliMatch algorithm for determining climate suitability and self-organizing maps, we ran the modeling under current and future climates. We started out with about 6,800 species that had observations on GBIF. And then this Venn diagram here is showing the overlap between the 3 different modeling components. So looking at current climate suitability, future climate suitability, and then the self-organizing maps. Any species that was picked up by any of these 3 models was then fed into the next stage of the analysis. So this represented over 3,000 species that we were able to narrow it down to, which isn't narrowing it down much, but it still is a drop of about 50% of what we started with. And on the right is just showing a hotspot map from the CliMatch algorithm, showing the number of potential species in our list that show climate suitability at given areas within Canada. And this isn't considering thermotolerance, it's just considering those bioclimatic variables. Now, when we run these climate suitability models with current and future climate, we can look at the difference in the number of species that can invade any given spot within Canada to then look at climate change risk for invasive grasses. So here is a heat map showing areas that are at higher risk of invasive grass invasions, shown in red, and lower risk, shown in blue. So we can see that generally in central and eastern Canada, there's probably going to be an increase in potential invasive species in those areas with climate change. And then in the west, there might be a decrease in some areas. When we take that climate information and combine it with data available from the invasive species databases that we can mine and feed it through our risk analysis tool, we end up with a list of 12 potential major invaders. So that risk analysis tool, it classifies species as potential major invaders based on the establishment spread score and the impact score that it receives. So it doesn't look at entry or geographic score. And that's why some species on this draft list have a pretty low geographical potential, but are still on there because that particular algorithm isn't considering the geographical potential. But we can see with this top 12 list that there are some species that have a reasonably high geographical potential, especially those first two. And what we've been doing in my team is trying to develop data exploration tools with these analyses as well. So I'm going to bring over an R-Shiny application that we've been working on to help explore this data set. So we can see this risk summary page. We can look at the actual values for the different score components if we want. But if you want to look at the information that's known about this species, so let's look at Imperata cylindrica, as this one's towards the top of the list. We can go and look at the climate suitability map just for that species, and that's under current climate. And if we want to see the areas that in Canada that may become more vulnerable to it in the future, we can look at the future climate suitability map. And because this is connected with invasive species databases, we can then look at the potential habitats where it's found. So we draw information from the CABI website and CABI databases. So we can see that its principal habitats here are cultivator agricultural land, managed forests, plantations, and orchards, and its status in those is harmful, pest, or invasive. So that tells us that this particular species could be a pretty big economic threat within Canada in those areas where it has climate suitability. There's additional details that we pull in here. You can look at the native range of the species based on that CABI information. So we can see that its native range is generally outside of North America, but it's widespread, which also helps tell us that it's potentially a major invader for Canada. So with that, I'm going to go back to the presentation and go over what our conclusions are from this work so far. So this quantitative horizon scanning can provide priority species for regulatory review, and it can be used to identify gaps in biosecurity for a given taxonomic scope while identifying climate change risks. Some of the key caveats that have been mentioned in other presentations, because we're using open source species occurrence data, there's biases in where those data are obtained. The availability and accessibility of data can be problematic. And there could be misidentifications of species, especially if we're dealing with plants or other cryptic species. And so This quantitative horizon scanning really represents a first pass that flags species for further review within our pest risk analysis process. And in terms of the next steps, the CFIA will continue the pest risk analysis process on the species that we've identified through quantitative horizon scanning. I think categorization has been completed on some of the wood-boring beetles. And I'm also leading Eufresco project. So Eufresco is a research collaboration organization that pulls together countries from across Europe and the rest of the world. And we're working on developing a flexible, internationally vetted method and framework, and creating open source toolkits for conducting horizon scanning. So if you're concerned with a particular province, state, or even county, we're going to build the tools to make it easy for you to run these scans. And so with that, that's all I had on this presentation. And I'm happy to answer any questions that people may have.
Awesome. Thank you so much, Joseph. That was really cool. We do have a couple of questions coming in. So people agree that it was a really neat talk. Does the screening tool consider socioeconomic impacts?
So that's one area of active work right now. Like I said, Megan Abergel and my team has been working on an ecosystem services data set that looks at socioeconomic impacts. So we already have areas of, I forget what they're called, they're ecoregions of importance based on, I think, the IUCN or World Wildlife Federation. I forget the exact provenance. That's what Megan's been working on, looking at national parks and provincial parks that are affected, as well as some information on labor statistics across counties. So you can imagine that, say you're looking at wood-boring beetles, for example, you probably want to know if those areas where the wood-boring beetles could invade, if they're going to impact, like how many jobs could be impacted there. So there are census statistics on that. So that's an area of active work. I don't have anything like that to show right now, but maybe in a future year, I will have some better information on that. But yes, we're working on that.
Awesome. Yeah, that'd be super valuable. How is climate risk scenarios factored into regulatory review decisions? What if low or moderate risk now based on climate data, but high risk later based on projections?
So that would be a question more for my policy and programs colleagues who actually do the drafting of regulations. Again, this horizon scanning and foresight aspect is fairly new, but I will say that the regular pest risk analysis process, when they're going through a formal risk assessment, they do run climate suitability calculations with current and future climate. So that is already considered. In terms of how this actually incorporated into the regulatory process, I'm not knowledgeable in that area. So I'm sorry, I can't speak to that.
No worries. Why might there be a possible decrease of invasive species presence in Western Canada, but an increase in the central or eastern part of the country?
So one thing that I didn't mention was the spatial resolution of the climate suitability maps. So each pixel in those pictures here, maybe I can go backwards to just show the map again. So each pixel here represents approximately 10 kilometers by 10 kilometers. And so when you get into Western Canada, we have the Rocky Mountains, which have massive elevational gradients across a 10 kilometer by 10 kilometer square area. So what's probably happening there is it's an artifact of the data resolution in that the climate information is being averaged across just a massive gradient. And so I would expect that the results for mountainous areas to be a little bit less trustworthy when it comes to things like looking at the broad scale climate risk, just because the data are so aggregated. We had to choose that resolution because it takes almost a week to run all the climate suitability maps for thousands of species. And so we had to balance our resolution with time and workload considerations.
Okay, awesome. Thank you. Let's see here. This person's asking if you can go back to look at old data for your predicting parameters, for example, the early 2000s, and see if that date predicts distribution of how current invasives are distributed, or how do you test the validity of your model?
So in this case, this entire framework is designed to try and identify potential quarantine pests. So in terms of validating this model, again, we're building this in a regulatory context. So the goal is to identify candidates for regulation. So the way that we're validating it is we are having our risk assessors go through these shortlists that we're developing and running through that categorization process. And so we consider it successful if we have identified a potential quarantine pest based on our method and if it agrees with the regular pest risk analysis process. Again, this is a foresighting tool, so it's meant to raise the early warning flag. It's not meant to, I think someone mentioned it earlier, it's something that's meant to be good enough. It's not meant to say definitively this is a quarantine pest or this isn't, especially because most of the information on these pests isn't mineable from an open source data set. So it's buried in the literature. And so this method won't pick up that information. I hope that helps answer your question.
Yeah, that makes sense. Kind of along the same line, somebody's asking, how do you represent uncertainty within the tool?
That's a really good question. We're working on it. So with the climate suitability, we can run some leave one out analyses to get a better estimate on uncertainty in the climate models. The self-organizing maps have protocols for looking at uncertainty, which we're working on including. And then calculating uncertainty is going to be one of the big topics within that Ufresco project that I'm leading. That's going to be a group effort to try and figure that out.
Awesome. This person here is talking about Japanese bloodgrass. It's sold via nursery trade. Will the CFA ask the industry to halt sales pending further analysis for those types of successful candidate species?
I can't speak to that. Again, that's in the realm of my policy and programs colleagues. I guess I neglected to mention I'm in science branch at CFIA, so we focus on the science, not so much the policy and regulations. We provide that science advice function to our policy and programs colleagues.
Yeah, so important. So many different branches at the CFIA.
Yeah.
How many of the species in your review are currently in the horticultural industry, and how many are new species not here yet? Would it not make sense to restrict the sale of these already available species?
So what I did for the invasive grasses analysis and for the wood-boring beetles is try to exclude any species that are known to occur or to be already established in Canada. That depends on a few things. It depends on lists of online lists of species that are known to be established in Canada to be up to date, as well as having open source observations on whether those species are in Canada. So in this particular case, that short list that I showed wasn't on any of those lists of species that are known to be established in Canada. Mind you, if Imperatus cylindrica is already in the horticulture trade, then that might suggest there's a data set that I've missed or that its presence just hasn't been reported in some of those data sources. So again, that also highlights one of those gaps in this analysis. We're working at such a large scale that if those data sets aren't fully up to date, or if we're missing a critical data source, there will be some species that filter into the list that might already be fairly widespread but underreported, or might not be suitable for following that pest risk analysis process.
Yeah, no, that sounds good. Thank you so much. So a couple comments here just saying nice talk, and I agree, did a really great job. I think we'll move on to your second talk, which will be all about the global pest outbreak detection system.
Okay, just give me a moment here.
No worries.
I'll share my screen again. Okay, so this second talk, this is work that was done by Josh Percy on my team. He is not here today because he is presenting the talk that I just gave at a conference elsewhere. So I'm going to be presenting the work that he has done on developing what we're tentatively calling the Global Pest Outbreak Detection System. We've already talked about this. Biological invasions are costly and as costly as natural disasters, which means that we really want to operate in that preventative space, which is a message that has been echoed today. Now, if we could set something up that has a global tracking and early detection to enable prevention, that could really help us here. So if we're looking at potential invasive pests and where they occur, there might be different pests of interest that occur in different regions of the world to help us figure out what we should be concerned with when we're importing things or traveling to those countries and returning. The Global Pest Outbreak Detection System, as we're calling it, aims to identify active or near future outbreaks happening internationally or domestically. It's built using R and R Shiny and relies on GBIF data and open source information. It's under active development, so some of the things that are presented here might be a little bit rough around the edges. I would like to ask you to just excuse those rough edges, as with some of this stuff, every time you make a change to an application, it can set you one step back. The overall workflow, though, contains 3 steps. We extract species occurrence data from GBIF and clean it, and then we forecast species occurrence data going to the next year, and then we try to detect outbreaks of species. For the GBIF data, we went with this data source because there's lots of species observations in there. It pulls information from government agencies, universities, colleges, and citizen scientists, and it has an API that lets you really pull data in a high throughput fashion. Additionally, and relevant to this particular project, that data is organized by global administrative areas, which is the unit of space that we're going to be working with this tool. So we extract the data from GBIF. Let's say we're looking at Japanese beetle Papillia japonica in Ontario, Canada. We look at the number of occurrences over time, and we can see in this particular case, it's increasing over time. And then we can try to forecast with several different models, trying to get models that line up best with the occurrence data and use those to forecast. So we have 3 different models here, and we can see there's 3 different estimates with errors on the forecasted number of occurrences. Now, how do we take that and turn it into an outbreak detection? So what we're currently applying are things called Nelson rules, which are methods in process control to determine whether some measured variable is out of control, whether it's unpredictable versus consistent. And there's 2 types of rules here, or 2 categories. The first is difference from the mean. So the first rule is if one point is more than 3 standard deviations from the mean, the process is out of control. Or if it's 3 standard deviations below. There's other rules, like if it's 2 points that are 2 standard deviations outside of the mean, then it could be a process out of control. And also patterns over time. If it's sequentially increasing, if all the points are on the same side of the mean. So we're using these rules to indicate whether we have an outbreak. And applying these rules to the plot that I just showed you, we have, starting in 2013, at least 6 sequential points that are increasing. And then starting in 2021, we have 4 points that are greater than 1 standard deviation from the mean. And so with this current outbreak detection algorithm, we could say that the outbreak started in 2013 and is continuing. And with our forecasting models, we expect it to continue into next year. So with that, I'm going to go to a live demo, and we will look at what this tool looks like in the actual application. So We start off on this screen, which shows a map with all the global administrative regions. I'll note some of the polygons are a little off because they've been simplified to simplified processing. I'm just going to set a few parameters here. So we have one Nelson rule, and we're going to look for any outbreaks based on these Nelson rules between 2022 and 2024. So we're going to update the map, and it's going to take just a moment as it runs through all of the calculations. So bear with me here for a moment. And then we get this map, which is color-coded based on the number of potential outbreaks. So again, this is all about potential outbreaks, not actual outbreaks. It's to raise that early warning flag, and then someone can follow up on whether there was an outbreak. So let's zoom in here on Ontario, since that's where I'm currently located. And we can see that between 2022 and 2024, there were 26 potential outbreaks based on the GBIF information. And if we look at it, we see species like hemlock woolly adelgid, Adelgis sugi, Agrillus planopennis, emerald ash borer. But we also see things that are obviously wrong, like Corma delicatula, because there are some strange interceptions. If you go to the CFIA public map on our website of spotted lanternfly detections, there are just some dead ones that had pictures taken that came from, say, like cruise ships or things like that. And so when we look at that, we can already see, okay, it's raising the flag, but there are some false positives here. And so we're working on figuring out how to address those false positives in this application. Now we can also look at time series maps. So if we go over to the interactive time series, and let's look at Cytolema perspectalis, as someone mentioned that in an earlier presentation, we'll let this update. And then we can look at what this tool is saying about potential outbreaks in Canada of this species. So I'll note a couple things. We're still working on data standardization and accounting for low numbers of observations for particular species. So in the case of Prince Edward Island, our rules are detecting an outbreak, but there were 3 observations. So that might be more indicative of a spread event rather than a particular outbreak or an early incursion. But if we look at Ontario, so these observations go into the hundreds, we can see that this is flagged in 2024, that there was an outbreak. And again, if we look at the pattern, there was probably an outbreak beginning before then. There's just this year 2022 where there seemed to be a reduction in observations, which meant some of those Nelson rules didn't pick it up. So our definition of what an outbreak does require some modification here. So with that, I'm going to pull that away, and we'll go back to this presentation. So in terms of GPODs, as we're calling in short, the goal here is to provide that early detection information of global pest outbreaks for expert review, where early detection is reliant on open source information. And then it could be used to identify spread events as pests move across administrative boundaries over time. And we could identify high-risk species or administrative areas that seem to have a lot of active outbreaks going on. We have some current limitations, obviously, in the data. These include a taxonomic bias, where these flashier species are going to be more reported than these more cryptic species. There's also a geographic bias in the GBIF data. In general, Western countries tend to have more active users. Areas of higher population density have more active users, and so on. So in terms of the next steps, we're looking at trying to adjust for sampling effort, which is proving a little bit difficult as to what we actually adjust with reference to. Right now, we focused on a subset of CFIA regulated species, but we're hoping to expand that to include species from international pest lists that we don't currently regulate. And we're working on improving the user interface and user experience of this application before we actually go and distribute it. And so we did come with some questions for the audience here that we'd like everyone to ponder, because we're working on eventually being able to share this tool probably through the Canadian Plant Health Information System. What other methods can we use to identify outbreaks? So right now we're using these Nelson rules, but perhaps there's other ways we can define what an outbreak is. And are there any other features, any other components related to pest outbreaks that might be helpful if you had access to a tool like this? So with that, that is the last of the presentation, and I am happy to take questions now.
Thanks so much, Joseph. Really appreciate it. I'm just looking on the chat here. If you have any questions for Joe, please pop them in the Q&A box. The first one here is asking if GBIF takes into account the data going into EdMaps and iNaturalist.
So I do know that GBIF imports the iNaturalist. Actually, there's a message in the chat that GBIF imports iNaturalist observations with compatible licensing. There is missing data that's on iNaturalist that doesn't go into GBIF when it doesn't have the right license. So we're not pulling that in right now. And EdMaps, I think, is separate. I don't think it feeds into GBIF at all from what I remember. So we haven't pulled that in. So this tool right now is just relying on those GBIF reports.
Awesome. Yeah, thank you so much. And thank you to Chris in the chat for filling that in too. This person it's not a question, they're just commenting that there's been a lot of spotted lanternfly sightings, but not necessarily an actual outbreak. But I'll just add that, yeah, it's important to continue reporting those types of things that you see on the landscape. It can really help databases like this and really help, CFA and other people go out and inspect those areas and respond quickly.
And I will note too that we're planning to expand to species that are of concern to the provinces and potentially even at a municipal level as well, and to create more of an inward facing tool as well for Canada going down to the county and municipal levels. And so at that point, it could be helpful for potentially identifying maybe there's some spread occurring of a species you're concerned about in a neighboring county or a neighboring municipality that you may not have picked up through like regular conversations with your colleagues that may be going into iNaturalist and GBIF. So it's really about raising those early warning red flags, and then we have to follow up, right? So there may not be an established population, but there may be sightings. So that might indicate that maybe there's a vector of entry into that area that we were unaware of, and we could follow up and see what is that vector and investigate.
Yeah, it's important to consider for sure. This person's asking, well, it's kind of a comment, but instead of having an outbreak category, have you thought about having like an incursions category so we have a warning well before an outbreak?
That's a really good idea. So we hadn't thought of that. We'd been thinking about spread, so when it goes to a neighboring administrative region, but an incursion idea, that's really good. Thank you for that. We haven't considered that, but I'm going to add it to our work plan right now.
Awesome. That's awesome. Let's see here. There's another question that came in. I'm wondering if there has been or if there could be benefit by coordinating with other federal departments like ECCC, NRCan, particularly to share data sets or subject matter expertise.
Yeah, so at CFIA, we have launched in this past year the Canadian Plant Health Information System. And so right now we've onboarded, I think, Agriculture and Agri-Food Canada and Natural Resources Canada, among others, including federal, provincial, and territorial partners. And I will pop a link into the chat that has a link to the CFIS webpage. There's an email address there where you can find out more. And we're just sort of diving into that space of enhancing collaboration of and sharing of data sets and analysis between departments, between partners, and so on through the Canadian Plant Health Information System.
Awesome. Okay, I think that's it for questions. So we'll wrap up there. But thank you so much, Joseph, for both presentations. They were really great.
Thank you.
And thank you to Nicole too. Thank you to all of our people attending here and watching. We really appreciate it. So with that, we'll close out the second horizon scanning session. We look forward to seeing you for the next session. It starts at 3:50. It's our Indigenous community session. So we'll see you all there.